Biologist. Today we are going to do an activity on types of natural selection. Yesterday we used Hardy-Weinberg and we identified how we could quickly tell an allele frequency shift by using the Hardy-Weinberg equation. That actually goes along with what we would identify as a single gene trait. So a trait that is determined based on a single gene. So for example, like right here, where I have a single gene trait, the brown fur versus the black fur. In 2000, you can see that the brown fur was low, black fur was higher. And then in 2020, the brown fur increased and the black fur decreased. And so you could say that something nature was selecting against the black fur mouse. Now, when we talk about a polygenic trait, though, we're not talking about black or white, black or brown. We're talking about a trait, a characteristic that has multiple outcomes. For example, human height. Human height is a great example of a polygenic trait. There's not just people who are 6 foot and people who are 5 foot. There are people who are every size in between, to very tall and very short. And so that's a polygenic trait. It means poly, many, means that it is a trait that is determined by many genes working together. Today, we're going to take a look at how does nature select based on a polygenic trait. And we call these things shifts. So we look at a population and we identify how is the population shifting over time. Are they evolving? Are they not? And so I want to start you with a graph, because a polygenic trait, if I were to have the class even get up in front of the class and line up, you would find that there would be really short individuals in our class and really tall and people all throughout the middle. Okay? Well, let's use, for the sake of this lab, the lab itself is going to be about snakes, but let's go ahead and use Darwin's finches. When Darwin found finches on the island, he actually found finches that had extra small beaks, and he also found them that had extra large. And he found some with large beaks and medium beaks and small beaks. And so there's a whole variety of outcomes. That is one of the indicators that you know it's a polygenic trait. The thing is, though, the outliers, the ones on the extreme, there are way fewer of those than the ones in the middle. And so typically you're going to have very few of these extra small, very few of the extra large. You're going to have a few more of the large, a few more of the small, but the majority is going to be right in the middle. And so when we connect this, you're going to end up with what we call a bell curve. If I took that, if I made a little bell here, took my curve that I just made, boom, made it into a little bell, right? So this is called a bell curve. Now, what's important for us in this lab is that when we collect data, we get to determine, okay, this is our bell curve, this is our this year. Then we go back in time, maybe 2 years later, 3 years later, maybe the next year, and we collect the same data. And then we graph it on top. And so let's say, for example, there's going to be 3 things that we're going to be looking for here. Let's say that this happens. Let's say I go back after a year or 2, and I find that there really are absolutely no extra small. So my extra smalls are gone. There are very few smalls. So something happened to the smalls. They're dying out. But if I look at the extra large, those have actually increased. And the large, there's just a ton of them. But the medium has decreased a little bit. And now we also have this extra, extra large beak. Because when the extra large beaks are mating, they're going to produce these extra, extra large. And so what you have here, you have the same pattern. But notice that it shifted in one direction. When the sequence, the distribution shifts in one direction, we call that a directional shift because it's moving in one direction. So this would be directional. Okay. Sometimes though, so what that means is that let's say that there was just a ton of rainfall and plants with really small seeds, they just didn't do very well. And so a lot of the seeds that were available to be eaten, they were large. Well, an extra small beaked bird, they're not going to be eating extra large seeds. It would not physically be able to. And so they die. The extra large beaked birds, they get their food, they get to reproduce, and they have more large alleles at all these different multiple gene sites that they end up even creating something larger. So that's directional. Stabilizing, let's talk about stabilizing. Stabilizing is exactly what it says, okay? It's going to make the population more stable. Stabilizing occurs when, let me redraw the original. So if I have my graph, and I have extra small and extra large and medium, a stabilizing shift means that we're just going to stabilize what's happening. And when we stabilize what's happening, what really it means is that there's not really going to be any extra small, there's not going to be any extra large. Their food source is not very good. However, the medium does really, really well. Okay? Small does a little bit worse, and we don't even have any extra small. Extra large we don't. We have a few large. And so what happens is we get this narrowing. That's called stabilizing. You're stabilizing that population. Now, in a lot of cases, you think, oh, this is great. However, you're also reducing genetic variability here. And so you're making it so when you reduce genetic variability in a population, you are actually making it more susceptible to the potential of extinction. And then the last type of shift, really quick, so I'll draw another graph. The last type of shift is known as disruptive. If you think of the word disruptive, you're disrupting it. And so here's my normal bell curve. That's how they're distributed. If I want to disrupt this, what that means is that, excuse me, what that means is that extra small beaked birds, they're doing really well. The large, they're also doing super well. However, they're doing really well because there are seeds that are really small that the extra small beaked birds can get. And then there are seeds that are really big that the big beaked birds can get. And so the extra small and the extra large beaked birds, they do not have to compete anymore. The medium ones are trying to compete with both, but are not doing a very good job. And so the medium-sized beak goes way down. And so what you see here is an M. That means that when we are creating this, as soon as this bottoms out, and there are none, look at what I do. If I take this and I cut these two in half, do I now have two bell curves? Absolutely do. And that's what can come from disruptive selection. Disruptive selection creates a disruption where the two extremes are meeting their needs in very different ways. And what that can do is that can make them become isolated by behavior. If they become isolated by behavior, that can lead to reproductive isolation. If I have reproductive isolation, then what that could lead to is speciation. A new species arriving from it. So today in this lab activity, what you're going to do is you are going to go through and look at data of 3 different sets of data. You're going to graph them, and you're going to identify, is it moving, is it shifting directionally, stabilizing, or disruptive? Now, just to get you started, make sure that you're looking at your data to know exactly like what numbers you should be using. So for example, right here, we're going to do the length is down here. Okay, and so we're going to start 2 centimeters, and this is in centimeters, so we'll do 2 centimeters. We'll do 3. No, we won't, because that's not a thing. Okay, so we'll do 2, 4, 6, 8, and 10. You could spread it out if you wanted to a little more. Over on this side, because we have to get, what's our highest? Our highest is 18. So I have to get up to 18, so I'm going to go by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This is the number. All right, so let's do $19.80. I'll do in pink. So in 2, I had 2. At 4 centimeters, there were 14 of them. 6 centimeters, there were 18. At 8 centimeters, there were 12. And at 10 centimeters, there were 4. Excellent. There you go. So that's 1980. Now, let's see what happens to it. Does it shift? So now we're going to do 1984. At 2, there were 4. And there were 12. At 6, there were 8. Eeks. And then at 8, there were 9. And at 10, there are 8. Okay. Now let's do the last one quick. We'll do the last one in 1988. We'll do green. I've already added the plots. And